All right. Previously, we talked about the simple gas laws relating pressure and volume and temperature and moles of a gas. When we change one of those variables, we see a change in the others. We can also apply all of those properties to a single equation. The ideal gas law looks at pressure, volume, temperature, and mole changes for a single gas substance. So if we know 3 out of those 4 values, we can find the 4th one. So frequently this is referred to as the PV equals nRT equation. So pressure times volume, you will recognize from Boyle's law. And then we have our direct relationships between pressure and temperature, as well as volume and temperature. And then our relationship between volume and moles. So we looked at each of those in the simple gas laws. Putting them all together, we get what's called the ideal gas law. So a gas that acts ideally does not have any force of attraction. Molecules are very spread out. The volume that the molecules occupy is very small compared to the distance between the molecules. And our idea about elastic collisions that we talked about with kinetic molecular theory. The one thing that we are adding this time is the gas constant. So if you remember, we had a combined gas law that looked at changing pressure, volume, or temperature. We are assuming an unchanged number of moles when we look at this, just changing the pressure or the volume of temperature for a single gas substance. We can also incorporate the mole idea in this, and we can see the relationship using the combined gas law. If each of these sides of the equation represent a single substance of gas, then they have to represent a constant value that is denoted as R. So R is the gas constant. So any ideal gas, we would use the same R value. Now the R value we're going to use requires certain units, and we'll look at that in the next slide. So we have to be very careful about the units we use with our ideal gas law. Now in our simple gas laws, we could have used any units of pressure, any units of volume, but in the ideal gas law, we have to use specific units, and one of those being Kelvin for our temperature. Remember, anytime we have temperature in our equation, it has to be in Kelvin. Now the value of R comes from our standard temperature and pressure, and we'll come back to this idea. Standard temperature and pressure, which is frequently denoted as STP. Standard temperature being our 273.1 or 0.15 Kelvin, all right, also known as 0 degrees Celsius, and our standard pressure being 1 atmosphere. If we fill these values in, so here's our pressure, here's our temperature, we're looking at 1 mole of a substance, and that 1 mole will occupy 22.4 liters. We'll come back to that idea later. We get an R value of 0.0821 liter atmospheres, right? Our pressure was atmosphere, volume in liters, so liters times atmospheres divided by moles times Kelvin. Alright, so these are our units for R. So that means our pressure must be in atmospheres, our volume must be in liters, our temperature must be in Kelvin, and then our N value is in moles. So we can put all these together for the units of R. Now the gas constant R changes numerical value if we change units. We are only going to be using this one for right now. So this is the only one you need to worry about, the 0.0821 liter atmospheres per mole Kelvin. But just to give you an idea, this table here shows the R values for different units. Alright, so this first one is the one we're interested in. But if you change the units of the volume to, say, meter squared or centimeter squared, or you change the atmospheres to torr or millimeters of mercury, you get a different value for R. Alright, we even had the conversion of liter atmospheres turning into joules. We have this one down here, and we'll come back to that one later. We will see that number again. But for our gas laws, our ideal gas law, we're just focused on this value of R in liter atmospheres per mole Kelvin. Alright, so let's try using our ideal gas law. What is the temperature of 0.05 moles of air that has a pressure of 1.5 atmospheres and a volume of 1.1 liters? Alright, so we're filling in the values that we know to try to find what we're missing. So in this one we're looking for the temperature, and we're given everything else. So we have 1.5 atmospheres, 1.1 liters, 0.050 moles, and we're going to use our R value, 0.0821, and we're going to solve for temperature. Alright, so multiplying everything on the left and then dividing by the moles and dividing by R gives us a temperature of 402 Kelvin. Alright, let's look at the second one. If a balloon has a temperature of 298 Kelvin and a volume of 1.98 liters, what is the pressure of 1 mole of the gas? Alright, so this time we're trying to find pressure. Let's see, we have 1.98 liters, 1 mole. R is exactly the same, 0.0821, and our temperature is 298 Kelvin. So this time we're solving for pressure, and we get 12.4, and remember it has to be atmospheres because we're using the R value. Alright, so we can solve for any of the 4 variables, pressure, volume, moles, or temperature, if we know the other 3. Alright, standard temperature and pressure. We will see this one more when we talk about stoichiometry, but standard temperature and pressure is given as 273.15 Kelvin, our standard temperature, and 1 atmosphere for standard pressure. So at this standard temperature and standard pressure then, 1 mole of any gas, 1 mole of any ideal gas should occupy 22.4 liters based on the R value. Alright, so we're solving this one for volume. We have 1 mole times our R times our standard temperature divided by our standard pressure gives us 22.4 liters. So this is frequently used as a conversion factor. 22.4 liters in 1 mole, or 1 mole is 22.4 liters. Alright, and we're going to see that again. Now, just to use this idea of standard temperature and pressure, we want to look at different types of gas. So if I have 1 mole of O2 gas, 1 mole of H2, and 1 mole of NH3, assuming they're all ideal gases, I'm going to occupy the same volume because it's 1 mole. So each of these would occupy 22.4 liters for the volume because there's 1 mole of each at STP, or standard temperature and pressure. But notice it's very different numbers of grams. And the grams are based on the identity of the gas. But the moles and the volume are not based on the identity of the gas. Now we can use this 22.4 liters per mole as a conversion factor at STP. But if we're at any other conditions, if it's not standard temperature or not standard pressure, we have to use the ideal gas law to calculate our volume or our moles. Alright, so let's try using the STP. We want to find the number of moles in a red balloon with a volume of 1.5 liters at STP. So here's where we can use our conversion factor. 1.5 liters times, we'll use our conversion factor of 1 mole over 22.4 liters. So our liters will cancel out and we'll be left with the moles. So we have 0.067 moles. It doesn't matter what the gas is. All that matters is what the conditions were. And at STP we have the conversion factor. So we don't have to use the PV equals nRT equation. Alright, let's look at more of a concept idea. We have 3 balloons. They're all at STP, each one containing a different gas. That is 14.8 liters each. How many grams of each gas would be present in the balloons? Alright, so 14.8 liters. At STP, we can use the same idea. 1 mole of any of the gases is 22.4 liters. Alright, so this allows us to calculate how many moles it would be. So all 3 balloons then would have the same number of moles. They'll have the same volume. So once we know the moles, then we're just multiplying by the molar mass. So for helium, we have 0.661 moles times 4 grams per mole. So helium would get us 2.64 grams. Carbon dioxide is a larger molecule, so 44 grams per mole would get us 29.1 grams of carbon dioxide in the balloon. And then ethane, same moles, multiplying by the molar mass. So this one would be 30 grams per mole. Gives us 19.8 grams. So the larger the molar mass, and in this case it would be the CO2 with the larger molar mass, the greater the number of grams, because they each have the same number of moles. Now we can use the ideal gas law and apply it to several different concepts related to gases. Density, because the density of a gas changes if we start changing its pressure or its temperature or its volume. So we can calculate the density of a gas given the variables. We can even identify a gas given how much space it occupies, given the pressure and the temperature at which it's occupying. And then we can look at stoichiometry using relationships between gases within a balanced equation. And then finally, partial pressures of a gas are also can also be determined based on the ideal gas law equation used to find either pressure or volume at a certain temperature. So we're going to look at examples of each of these. Alright, So just to go back over the idea, standard temperature and pressure, our volume is always 22.4 liters for 1 mole of any gas. So the volume and the moles would be the same regardless of the identity of the gas, but the grams would be very different. So we just saw that with our previous calculation with our grams in the balloons. This shows the same idea using helium and nitrogen and oxygen. So notice our mass is very different. Even though our volume is exactly the same, our temperature, our pressure, and our moles exactly the same, number of particles exactly the same. So everything we see in the brown area are the same between the gases. But because the molar masses are very different, this changes the density. Each of these gases has a very different density. So we define density based on mass per unit volume. So despite the fact that all the volumes are the same, the masses are very different, and that's going to give us different densities. We can use the ideal gas law to actually solve for the density of a gas. So starting with our PV equals nRT, all right, we're going to manipulate this so that we have moles over volume. All right, moles over volume. So I'm going to divide both sides by V and then divide by RT. All right, so when I do that, I have N divided by V is equal to my pressure divided by RT. Then we're going to multiply by the molar mass, because density is grams per liter, or mass per unit volume. And right now we have moles per unit volume. So how do we turn moles into mass? We multiply by the molar mass. So that's what we're going to do. If we multiply by molar mass on both sides, here's my moles per volume times my grams per mole. So this is molar mass. All right, this right here is molar mass. And when I multiply by molar mass on the right side, it's listed as mm. Now we want to solve for density on the left side, which is our grams per volume. All right, so this right here is density. And we do that by multiplying the values that we don't need. Okay, so simplifying gets us these crossed out. N times moles, because N is moles, leaves us grams per volume. So that equals our pressure times our molar mass over R times T. This gives us equation for density. Density is equal to pressure times the molar mass of the gas divided by our gas constant R times temperature. So I can apply this to any of the ideal gases. So what is the density of CO2 at 0.97 atmospheres and 247.95 Kelvin for my temperature? Alright, so density is going to be equal to 0.970 times molar mass of carbon dioxide is 44 grams per mole. Alright, so we can easily find that. Divided by, we're using the same R value that we had before, our 0.0821, and our 247.95 Kelvin for our temperature. Alright, so when we do this, we get a density of 2.1 grams per liter. Alright, so that would be the density of the CO2 gas under these conditions. So notice for a gas, density can change. If I change my conditions, if I change my pressure or I change my temperature, it will change the density of my gas. Alright, let's look at the second one. What is the density of carbon tetrachloride, so CCl4, vapor at 714 torr and 125 degrees Celsius? Alright, so same equation, but we remember that we need to look at units. Alright, we're looking for the density, so I need my pressure, but I need it in atmospheres. Because we're using R, we have to have atmospheres. So I'm going to take my 714 torr and divide it by 760. Okay, and this will give me atmospheres. Torrs per atmosphere. Alright, then my molar mass. So for carbon tetrachloride, we can look at molar mass, 153.82 grams per mole. And we're putting that over R. And our temperature has to be in Kelvin. So we're going to add the 125 Celsius to our 273.15, so 398.15 Kelvin. Alright, so 714 divided by 760 is going to get me 0.94 for my atmospheres. Alright, times my molar mass divided by R divided by temperature gives me 4.42 grams per liter. Alright, so we can manipulate the ideal gas law into an equation for density for any ideal gas. Using the same idea, we can also find molar mass. So we have a gas held at 2.4 atmospheres, 300 Kelvin. Volume is 7.5 liters. Gas has a mass of 27.78 grams. What is the molar mass? Alright, so we're going to do this two different ways. The first is using our density equation. So density is equal to pressure times molar mass over R times T. So the one we were just using. Our density then is going to be 27.78 grams per 7.5 liters. Alright, so remember grams per liter is our density. Then I have 2.4 atmospheres for the pressure. I'm trying to solve for molar mass over my R value times my 300 Kelvin. Alright, this allows me to solve for molar mass, because that's my only variable that I have left, and I get 38 grams per mole. Alright, so that's using the equation we just found. We can also use PV equals nRT for this. Alright, in this case we're going to be solving for moles. So we would have 2.4 atmospheres. We would have 7.5 liters equals N, because that's our variable this time. We have R, and we have temperature. Alright, so solving for N, we get .731 moles. And then to get molar mass, if you remember, is grams per mole. So 27.78 grams per 0.731 moles. Gets us the same thing, 38 grams per mole. So you can use either method. Obviously in this one, using the density equation was a little bit quicker. It's really just one step, whereas using PV equals nRT for this one would be two steps, finding N and then finding molar mass. But either one will get you to the same answer. Alright, let's look at the second one. A gas exerts a pressure of 0.892 atmospheres in 5 liters. The density of the gas is 1.22 grams per liter. What is the molar mass? So again, I'm going to use the density equation first because we're given density 1.22 grams per liter. We have our pressure, and I'm looking for molar mass. I'm going to put R on the bottom. And then our temperature, 15 degrees Celsius. We're going to add that to the 273.15 to give us our total temperature. And then molar mass is going to be equal to 32.3 grams per mole. Alright, so notice in this equation, I didn't have any use for the 5 liters. So sometimes there is extra information there. But the 5 liters was also added so that you can actually use PV equals nRT, find the moles, but then you would also have to find the total grams. Alright, so trying to figure out one way or another, it's really about what you're comfortable with. Some ways are a little bit quicker than others, but you need to understand it. So using PV equals nRT, I can solve for moles. So this gives me 0.1885 moles. And then I'm going to have to use the volume times the density to get total grams. So I have 5 liters, that's 1.22 grams per liter. Okay, so 5 times 1.22. Alright, so that's 6.1 grams. So molar mass would be 6.1 grams per 0.1885 moles. And that gives me the same molar mass of the 32.3 grams per mole. So either way, but sometimes the density equation is a little bit quicker. So whether you're solving for density or solving for molar mass. But you can always go back to the PV equals nRT if that makes more sense to you. Alright, let's look at stoichiometry then. Hopefully you remember stoichiometry from 1211, where we can look at mole relationships in a balanced equation to turn our grams into moles, then our moles back into grams of something else. Now we're going to incorporate gases. So frequently we have gases in our balanced equation. So we can incorporate gases into our mole ratios to determine how many liters of a gas we have, or maybe what is the pressure of the gas. So let's look at an example. Magnesium reacts with oxygen to form magnesium oxide. How many liters of oxygen gas at 1 atmosphere and 25 degrees Celsius are needed to react with the 8.20 grams of magnesium? Alright, so like any other stoichiometry equation, we're going to start with what we have, which is our 8.20 grams of magnesium, and we're trying to figure out liters of oxygen gas. So I need to relate my magnesium to the oxygen. So the first thing we need to do is turn our grams into moles. So using periodic table and the molar mass of magnesium, we can turn our grams into moles. Then we're going to use our mole relationship with the O2. So I have 1 mole of O2 per 2 moles of the magnesium from the equation. And I'm going to start here and calculate moles of oxygen. I know I need liters, but having moles lets me calculate the liters based on conditions. Alright, so here's my moles of O2. Now I'm going to use the other conditions to find my liters. So we are going to use the PV equals nRT. So our pressure is 1 atmosphere. Solving for volume, we're going to plug in the moles we just found times R times the temperature. So 298.15 Kelvin. Alright, so when we calculate this, then we're looking for the volume, and we get 4.13 liters for the volume that the oxygen is going to occupy. Alright, so we need 4.13 liters of the oxygen gas under these conditions to react with the 8.2 grams of magnesium. So this is a two-step process, using the stoichiometry from the balanced equation to get moles, and then using those moles and the ideal gas law equation to find the volume. Now sometimes there's a simpler, quicker method. So STP allows us to use a conversion factor. Alright, so let's see if we can do that with our stoichiometry. How many liters of O2 at STP are produced when 2.44 liters of NO2 at STP are reacted with excess water? Alright, so we have a single set of conditions. We're not changing those conditions. We're just comparing our O2 with our NO2. Alright, so I'm going to start with my 2.44 liters of NO2. Now, just to show you the mole conversion first, I'm going to use the 22.4 liters in a single mole of NO2 to convert to moles. Then we want to do our mole relationship with O2. So 7 moles of O2 per 4 moles of NO2. Alright, and I'm looking for liters, and we're at STP, so I can now turn this back into liters with my 22.4 liters per mole. And notice what happened. We divided by 22.4 here, and then we multiplied by it. So I'm going to cross those out because they're going to cancel out anyway when I do my math. So using volumes directly, if we have the same conditions, whether they're STP or something else, we don't need to convert to moles. We can use the liters, the 2.44 liters, directly times the mole ratio in order to get liters out. So if I'm starting with liters, I can get liters out just using the mole ratio. I don't have to convert to moles because I'm not changing conditions. Alright, so this gives us 4.27 liters of O2 that are required, that are produced. Alright, this table gives you several different examples you can work through, looking for either volume of Cl, mass of aluminum chloride, given different conditions. I'm not going to work this out here, but I am going to work this out in a separate document that you can look at later. But it gives you several things that you can practice figuring out what approach would be best. Alright, so here is our flow chart for our stoichiometry then. Very similar to stoichiometry we've done previously, looking at mole-to-mole ratios, and then incorporating a new conversion factor with our 22.4 liters per mole. So starting with the mass of a substance, we can convert to moles. Once we have moles, we can do a mole-to-mole relationship and go back to mass of that second reactant or product. Or if we're working with gas laws, we can convert the moles of the gas into volume using either STP conditions in our conversion factor or using the ideal gas law. So you're familiar with 1, 2, 5, and 6. Now we're just adding a second layer that's very similar if we have gas laws. Once we go to moles, we can also turn the moles into volume. Alright, our last application is called Dalton's laws of partial pressures. And this has to do with creating mixtures of gases. If I mix more than one gas together, more than one gas could be 2, it could be 5, it could be 500. It doesn't matter how many gases you mix together. Gases are infinitely mixable. But what we see is an additive nature for the total pressure. Every gas maintains its own pressure given the conditions, and when I mix those gases together, it's an additive cumulative effect on the total pressure. So in the picture we have gas A occupying a certain pressure, and then gas B separately occupying a different pressure. And when we put A and B together in a mixture, we are adding the pressure of A plus the pressure of B to get the new total pressure of the gases completely mixed. Alright, so this indicates that I need to know the total pressure of a mixture of gases if I want to find out the partial pressure of each, because they're additive. So essentially, pressure of A plus pressure of B equals pressure total. So I need to know this total pressure, and then I can work my way backwards to finding out these partial pressures. Now the partial pressures that we have for the total are referred to based on mole fractions. So I need to know the mole fraction of each gas. Now mole fraction is defined as moles of a gas divided by total moles of all the gases combined. This is mole fraction. And that's exactly what this says down here. So N is the number of moles, and in this case the example is N2 for our gas. So moles of N2 divided by total moles in the system. If our system only contains nitrogen and oxygen, then we would have the moles of nitrogen plus the moles of oxygen to give us our total moles. Alright, let's put some numbers with this then. If I have 3.14 moles of nitrogen, 2.66 moles of oxygen, and a total pressure of 15 atmospheres, what is the partial pressure of each? Alright, so our partial pressure, which is normally indicated by the large X, of N2 would be the 3.14 moles divided by our total moles, so 3.14 plus the oxygen. This would give me my ratio or mole fraction of the nitrogen in the system. And then in order to get partial pressure, okay, we're working up here, partial pressure is equal to my mole fraction times total pressure. So 0.541 is my mole fraction, so the last thing I need to do is multiply by the total pressure of 15 atmospheres to get a partial pressure of 8.12 atmospheres for the nitrogen. Alright, we're going to do the same thing for oxygen. Mole fraction of O2 is equal to the 2.66 moles of oxygen divided by the total again. Okay, so for oxygen I get 0.459 for my mole fraction, and then multiply by the total pressure gives us 6.88 atmospheres. And if I only have two gases, adding up my two partial pressures, 8.12 plus the 6.88, should give me my total pressure for the mixture of 15 atmospheres. Alright, so the partial pressures of each are additive to give the total pressure for the mixture. Alright, so for this calculation, in order to find partial pressure of a gas, I need to know mole fraction of the gas, and I have to know the total pressure of the entire system, of the entire mixture. So part of using our ideal gas law might be to find that total pressure. So we have to look at how we can get these two components in order to find partial pressure. Alright, so let's look at an example with our stoichiometry and partial pressure. Alright, we have 75 grams of water. The total gases were collected, so you can see our reaction, our liquid is turning into gases. So we're collecting the H2 and the O2 gases for a combined pressure of 1.46 atms. So this is going to be my total pressure. That's one of the things we need for partial pressure. And the temperature is 275 Kelvin. What is the partial pressure of O2? Alright, so we're going to start with the 75 grams of water because we need to know how many moles we have of O2 and of H2. Because if we're going to find the partial pressure of O2, we're going to need to know the mole fraction of O2 times our total pressure of 1.46. Alright, so we're missing this mole fraction part. So I need to calculate my moles, starting with the 75 grams. We're going to divide by the molar mass for water. Then we're going to compare the water to the O2. So 1 mole of O2 is 2 moles of water based on the balanced equation. Alright, so let's look at how many moles we have now. We get 2.083 moles of O2. Alright, now look at our mole relationship. We have a 2-to-1 relationship between H2 and O2. So if I made 2.083 moles of O2, I can calculate how many moles of H2. Alright, so 1 mole of O2 is 2 moles of H2. I'm going to have twice as many moles, 4.167 moles of the H2. Alright, so now when I want my mole fraction of O2, I'm putting moles of the oxygen on the top, divided by my total moles, oxygen plus the hydrogen, on the bottom. Alright, and then this gives me my mole fraction. So this is mole fraction for the O2. Now my partial pressure of the O2 would then be my mole fraction times the total pressure for the mixture. So this is 0.487 atmospheres for the O2. Alright, we can calculate partial pressure of the H2 as well. Same idea. We can get the mole fraction by putting the 4.167 on the top. Once we have mole fraction, we can multiply by the 1.46 atmospheres. Also, since we only have the two gases, I could also take 1.46 minus the pressure of the O2 and figure out what's left over. So 1.46 minus 0.487 means 0.973 atmospheres would be the partial pressure of the H2. Alright, so we can use stoichiometry in order to find out how many moles we have. We can then get mole fraction, and then once we have mole fraction, we can use the total pressure to find partial pressure. Let's look at one other example where we don't have total pressure. This time we have a mixture of three gases, H2N2 and NH3. They're all mixed together, 25-liter container, 150 degrees Celsius. And we know how many grams of each gas are in the mixture. So we have grams. What is the partial pressure of each gas? Now notice also I don't have a total pressure. I don't have mole fractions. So I need to find both of those in order to solve this problem. Now since I do have grams, I can calculate moles. If I can calculate moles, I can get mole fractions. So we're going to start there. So 13.9 grams of H2 dividing by the molar mass. Alright, so we get 6.95 moles of H2. So that's one of them. We want to do the same thing for our N2 and for our NH3. So our N2 we have 64.8 grams. Divide by the molar mass. So that gives us 2.31 moles of N2. And then our ammonia, 78.7 grams, divided by molar mass. Alright, so that gives us 4.63 moles of ammonia. So now I have moles of everything. So let's add up all of our moles. So 6.95 plus 2.31 plus 4.63. Alright, if we add up all of our moles, we get 13.89 total moles for the mixture. Alright, so let's look at getting our mole fractions. So mole fraction of H2 is going to be the 6.95 over the total. Alright, so 6.95 divided by the total. Gives me 0.5 for H2. Mole fraction of N2, 2.31 over 13.89. Gives me 0.166 for my mole fraction. And then for ammonia, And ammonia, we had 4.63 moles over the total. Is 0.333. Alright, so there's all of our partial pressures. Now we need total pressure if we're going to find partial pressures of these. So in order to find total pressure, we're going to go back to the ideal gas law. Pressure times the total volume, 25 liters, equals, we're going to use total moles, so we're going to treat the whole thing as one gas, times R, times the temperature. So we had 150. We want to turn that into Kelvin. So that's 423.15. And now we're solving for pressure. This will be the total pressure for the whole mixture, because we treated everything like it's all one. And this gives us 19.3 atmospheres. So 19.3 atmospheres for our total pressure. So now if I take each of my mole fractions and I multiply by the total pressure on each one, I will get the partial pressure. Alright, so for H2 I have 9.66 atmospheres. For N2 I have 3.21 atmospheres. And for ammonia I have 6.43 atmospheres. And remember, when we add all of those up, we should get the total 19.3 atmospheres.